Welcome to Deep Dive into Knowledge.
Deep dive into knowledge. Consider for a moment the simple act of tapping a pane of smooth glass. You might be sitting in a quiet room, or perhaps resting on a train journey, or simply waiting for a light to change at a crossing.
Yes, a very common scenario.
You lift a finger, you touch a cold, unyielding surface on a screen, and you wait. You wait for a message to arrive or an image to appear.
Quite.
It is an entirely ordinary human experience, one you likely repeat hundreds of times a day without a second thought. Yet beneath that perfectly smooth surface, something profound and slightly unsettling is taking place.
Indeed it is.
We go about our daily lives entirely dependent on an invisible, silent reality that is happening millions of times a second just beneath our fingertips. It is a reality made entirely of pure mathematics.
Right.
There are no moving gears in that glass, you see. No physical switches clicking back and forth. There is only a microscopic architecture of logic, quietly processing sequences of numbers at speeds that defy human comprehension.
It is quite staggering when you really pause to think about it.
It really is. We carry these ordinary devices in our pockets, treating them as simple tools, yet they hold within them a deeper, almost overwhelming pattern of human ambition. They represent a silent legacy of an ongoing attempt to capture thought itself and render it physical. When you pause to observe this dependency, the paradox becomes clear. We have surrounded ourselves with a mirrored surface of absolute mathematical precision, yet we experience it as color, as music, as human connection.
Yes, the math is entirely hidden from us.
Exactly. We look at the glass and we do not see the mathematics at all. We only see the reflection of our own world handed back to us. So today we are going to trace a remarkable journey.
I'm looking forward to it.
We will explore how humanity moved from the exhausting physical burden of mental labor through rooms filled with monstrous metal gears to the invisible realm of quantum mechanics, all to understand why this digital reflection exists in the palm of your hand.
It is a vast trajectory.
It forces one to wonder about the origins of this strange relationship. If the digital world we touch every day is just an illusion hiding layers of mathematics, why did we first feel the need to build a machine to do our thinking for us?
Well, to understand that ancient urge, you really have to look at the immense burden of the human mind before these machines existed. We often forget that mathematics, for the vast majority of human history, was an intensely physical and exhausting labor.
Right, it wasn't just abstract thought.
No, not at all. It was slow, it was incredibly expensive, and above all, it was dangerously prone to human error. In the eras before computation was mechanized, the word computer did not refer to an object sitting on a desk.
It was a person, wasn't it?
Exactly. It was a job title. These were typically women sitting in large, quiet rooms, working in tightly coordinated teams to perform assembly line arithmetic.
When you say assembly line arithmetic, what did that actually look like in practice? I mean, were they just solving standalone equations?
No, it was much more fragmented than that. They were breaking down massively complex calculations into tiny sequential fragments.
I see.
One person would calculate a small piece of an equation, write down the result, and physically pass that piece of paper to the next person at the next desk. It was an industrialization of thought, essentially. Governments and militaries relied entirely on these human computers to compute things like artillery firing tables.
And the stakes for those specific calculations, I suppose, must have been extraordinarily high. If a machine makes a mistake today, an application simply crashes. But, well, what happened if a human computer made an error?
The consequences could be absolutely catastrophic. If a human being grew tired or simply suffered a momentary lapse in concentration and dropped a single carried number in a complex trajectory calculation.
Just one number.
Just one. An artillery shell would miss its target entirely. It could land on Allied positions or civilian areas. Furthermore, scientists attempting to solve complex differential equations that describe how things change over time, such as fluid dynamics or the transfer of heat, well, they might spend weeks or even months on a single problem.
Just grinding through the numbers.
Yes, they were entirely constrained by the limits of human stamina. The desire to automate this process was not born out of convenience or laziness. It was born out of a desperate need for absolute accuracy in high-stakes environments.
Listening to you describe the physical toll of that environment, an image comes to mind. Human brains are fundamentally exquisite creative engines.
Mm.
They are built for synthesis, for emotion, for sudden leaps of intuition. Forcing a human mind to perform relentless, repetitive arithmetic feels rather like taking a thoroughbred racehorse
Yes, quite.
and forcing it to pull a heavy agricultural plow. The creature can do it, certainly, but it is a tragic misuse of its true capacity. And eventually, the mind, just like the horse, will simply break down from the sheer grinding monotony of the task.
That is a very precise framing. The human mind rebels against perfectly uniform repetition, and the urge to relieve that specific burden is surprisingly ancient.
How ancient are we talking?
If we look back to Mesopotamia, around 2400 BCE, we find the abacus.
Ah, right.
It was the first mechanical aid for computation, allowing a person to perform addition and subtraction simply by moving physical beads along rods.
But the abacus still requires a human to know how the arithmetic works. Surely, it just holds the numbers in place, doesn't it?
Exactly. It is a memory aid as much as a calculating tool. You still have to know the rules of addition to use it.
Right.
But it is a testament to the sheer elegance of the abacus and the difficulty of improving upon it that it remained the dominant calculation tool for over 4,000 years.
4 millennia. That is astounding.
It is. The true foundation for moving beyond the abacus, for actually offloading the rules of mathematics themselves, arrived much later. In the 9th century, a Persian mathematician named Abu Ja'far Muhammad ibn Musa al-Khwarizmi wrote Arabic manuscripts that were eventually translated into Latin in the 12th century.
And what did those manuscripts contain?
These texts gave medieval Europe a systematic step-by-step method for solving equations.
And his name is the root of the word algorithm, isn't it? But what exactly does that mean in this context? How do we move from a philosophical concept of mathematics to a practical algorithm?
Well, an algorithm is simply an unambiguous step-by-step recipe for solving a problem.
The recipe.
Yes. Before Al-Khwarizmi, mathematics was often approached through intuition or geometry. His work established that you could break a complex algebraic problem down into a rigid sequence of simple, repeatable steps.
So you don't need the intuition anymore?
Precisely. It does not require intuition. It only requires following the rules in the correct order. Without that structured, sequential approach to problem solving, there would have been no framework for eventually instructing a machine to take over the burden of thought.
So once we had the recipe, so to speak, when did we first attempt to build a machine that could actually cook the meal? When did we try to turn those mathematical rules into physical mechanics?
That shift began to take shape in the 17th and 18th centuries, when inventors realized that this mechanical drudgery could literally be handed over to actual mechanics.
Meaning physical gears and levers.
Indeed. Blaise Pascal built the first true mechanical calculator in 1642, known as the Pascaline. 30 years later, in 1672, Gottfried Wilhelm Leibniz improved upon it with a machine capable of multiplication and division.
But how does a machine made entirely of brass and iron actually multiply numbers? I think we often take for granted that a physical gear can somehow represent abstract logic.
It relies on the geometry of the physical parts to enforce the rules of arithmetic.
How?
Imagine a gear with 10 teeth, each representing a digit from 0 to 9. When you rotate that gear past the 9, a physical peg on that gear catches the tooth of the gear next to it, pushing it forward exactly 1 notch.
Ah, I see.
That physical movement is the mechanical equivalent of carrying a 1 to the 10s column. Multiplication is simply achieved by mechanisms that rotate those gears repeatedly.
But these early devices were just calculators, weren't they? They could add and multiply, but they couldn't make decisions. When did the ambition shift from merely building a better abacus to creating something that could follow an entire sequence of complex instructions?
That brings us directly to the Victorian era and to Charles Babbage. Babbage was a British mathematician who became intensely frustrated with the constant errors he found in printed astronomical tables.
The tables calculated by those human computers we discussed earlier.
Exactly. He spent decades designing something he called the analytical engine. Unlike the simple calculators of Pascal or Leibniz, Babbage's machine was designed to theoretically perform any calculation, provided it was given the right instructions.
He never actually managed to build it, did he?
No, he did not. His funding from the British government eventually ran out, and the precision engineering required to manufacture thousands of interlocking gears without excessive friction was arguably beyond the capabilities of Victorian manufacturing.
So it remained a concept.
Physically, yes, but the detailed blueprints existed. And it was his collaborator, Ada Lovelace, who truly saw what those blueprints meant. In 1843, Lovelace, a brilliant mathematician and the daughter of the poet Lord Byron, wrote an algorithm specifically for Babbage's unbuilt machine.
And what was it meant to calculate?
It was designed to compute Bernoulli numbers.
I have heard that term, Bernoulli numbers. But for those who aren't deeply immersed in mathematics, why is that specific calculation so significant?
Bernoulli numbers are an incredibly complex, deep sequence of fractions used in number theory. Calculating them by hand requires an exhausting chain of sequential arithmetic, where the result of one equation is required to begin the next.
So it compounds.
Exactly. If you make a single error early in the chain, every subsequent number you calculate will be wrong. Lovelace wrote a set of instructions detailing exactly how the analytical engine's gears should be configured and sequenced to compute this chain flawlessly.
And that was the breakthrough.
Yes. In doing so, she essentially wrote the world's first computer program.
But what fascinates me is that her contribution was not just mathematical, it was profoundly philosophical. How does a human mind in the 1840s conceive of software for a piece of hardware that does not even exist yet?
It requires a rare capacity for abstract thought, the ability to decouple the logic of a system from its physical form.
Decoupling the logic from the metal?
Yes. Lovelace was able to see past the brass gears and the steam power of her era. She understood something that even Babbage himself had not fully grasped.
Which was what?
She realized that if a machine could manipulate numbers according to a rigid set of rules, it could manipulate any symbol. If you could mathematically encode musical notes or letters of the alphabet as numbers, the machine could compose music or process language.
Oh, wow.
She envisioned the concept of general-purpose computing a full century before such a machine was physically possible.
She saw the underlying architecture of information processing independent of the metal, but the physical reality of her time simply could not support her vision.
No, the engineering just wasn't there.
So we had this brilliant theoretical framework resting on paper for roughly 100 years. What finally forced the physical machine into existence?
The absolute physical urgency.
Yeah.
The theoretical calm of the 19th century gave way to the brutal realities of the Second World War.
Right.
The military requirements for rapid, complex calculations, for ballistics trajectories, for aerial navigation, for breaking encrypted codes became a matter of national survival.
So the government stepped in.
Indeed. In 1937, a graduate student in applied mathematics at Harvard University named Howard Aiken was struggling with his doctoral research. His work required solving nonlinear differential equations that model complex, chaotic systems where changes depend on the state of the system itself.
Which would have taken years by hand.
Precisely. Aiken drafted a proposal for an electromechanical calculator, took it to Thomas Watson, the president at IBM, and secured funding. The result, completed in 1944, was the Harvard Mark I.
What did the physical reality of that urgency look like? When we say a machine was built in 1944 to solve these problems, what are we actually picturing?
You must picture a monster of metal. The Mark I was 51 feet long, 8 feet tall, and weighed 5 tons.
5 tons?
Yes. It contained 750,000 individual parts connected by 500 miles of wire. It was a towering, deafening panel of polished steel and glass, filled with rotating shafts, electromechanical switches, and counterwheels. It was immediately classified as a wartime asset by the United States Navy.
Wait, 5 tons of steel and glass just to do arithmetic. Was it even fast enough to justify that scale?
Well, by modern standards, it was painfully, almost comically slow.
How slow?
It took 6 seconds just to perform single multiplication.
6.
Division took 15 seconds. A complex logarithmic function could take over a minute of loud physical grinding as the clutches and gears engaged.
If it took 6 seconds to multiply 2 numbers, it sounds like an evolutionary dead end. Where was the actual breakthrough?
The breakthrough was not in its physical speed, but in how it was instructed. The instructions were fed into the machine via a continuous loop of paper punch tape.
Paper punch tape?
Yes. This physical tape encoded the sequence of operations. A mechanical sensor would feel for the presence or absence of a hole in the paper, which would in turn open or close an electrical circuit.
Listening to this, it feels almost like a massive player piano.
Exactly.
The Harvard Mark IV, for all its 5 tons of steel and hundreds of miles of wire, was merely the unthinking instrument. It was the wood and the strings. The paper punch tape fed into it was the sheet music. The machine itself held no intelligence. All of the actual thought, the intent, the logic resided purely in the holes punched into the paper by a human hand.
That is a perfect analogy. And just like a player piano, if you wanted to play a different song, you do not rebuild the piano. You simply swap the paper roll.
That is profound.
It represented a monumental philosophical shift. Up until this point, a machine's function was entirely dictated by its physical shape. But with the punch tape, the hardware was decisively separated from the software.
Proving that the behavior could be changed without altering the structure.
Exactly. Grace Hopper, a brilliant naval officer and mathematician who worked on the Mark I, championed this separation. She later invented the first compiler, a program that translates human-readable code into the numeric machine language the hardware understands.
She is a legend in the field, isn't she?
She is. Incidentally, her team also famously documented the first literal bug in a computer. An actual moth had flown into Relay 70, Panel F, causing a physical malfunction. They taped the moth into their logbook.
But mechanical switches and electromechanical relays, even controlled by punch tape, are still bound by physical friction. They wear down, they take time to move. How did we escape the physical wear and tear of moving parts?
By abandoning physical movement entirely and turning to the instantaneous speed of electrons. While that electromechanical player piano was slowly grinding through its operations at Harvard, a completely different approach was being developed in absolute secrecy at the University of Pennsylvania. John Mauchly, a physicist, and J. Presper Eckert, an electrical engineer, were building a machine called ENIAC, the Electronic Numerical Integrator and Computer, completed in 1945.
What does it mean to calculate with electrons? How did they replace the physical switches?
They used electronic vacuum tubes. A vacuum tube is essentially a glass bulb containing a vacuum and metal electrodes. It allows you to control the flow of electrons perfectly.
So no moving parts at all?
None. By applying a small voltage to one part of the tube, you can permit or block a massive current from flowing through the rest of it. It acts as a switch, turning on and off, representing a 1 or a 0, but it does so without any physical moving parts.
And because of that?
Because it used electrons instead of physical relays, the leap in speed was astronomical.
What was the scale of ENIAC compared to the Mark I?
It was staggering. ENIAC filled a 1,500 square foot room, weighed 30 tons, and consumed 150 kilowatts of electricity.
30 tons?
Yes. It contained roughly 18,000 of these fragile vacuum tubes, along with thousands of crystal diodes, resistors, and capacitors. Where the Mark I could manage perhaps 3 additions per second, ENIAC could perform 5,000.
What was an instrument of that magnitude actually used for in 1945?
One of its very first serious computations was conducted by the mathematician John von Neumann, who used it to study the feasibility of the hydrogen bomb.
Right, the stakes were incredibly high.
Indeed. Von Neumann realized that ENIAC could compress calculations that would have taken a team of human computers centuries to complete into a matter of days. Furthermore, observing the limitations of ENIAC, von Neumann formulated the concept of the stored program computer.
What was ENIAC's limitation if it was that fast?
It had no memory for its own instructions. Changing its program required teams of engineers to spend days physically rewiring its plug boards and cables, essentially rebuilding the machine's pathways for every new problem.
So they were back to rebuilding the piano, in a sense.
Precisely. Von Neumann's architecture proposed placing both the program instructions and the data into the same addressable electronic memory. That specific blueprint, the von Neumann architecture, underlies virtually every single computer built over the last 8 decades.
There is a remarkably dark paradox woven into this era. Humanity marshaled its greatest resources to build a 30-ton giant brain, consuming enough electricity to power a small town, specifically to calculate the physics of a thermonuclear weapon, a tool of ultimate destruction. Yet, the society that built it remained entirely blind to the brilliance of the human minds that actually made the machine function. I am thinking, of course, of the women who operated it.
Yes. The omission of the women who programmed ENIAC remains one of the most striking oversights in the history of technology.
Tell me about them.
There were 6 women primarily responsible for this monumental task. Jean Jennings, Marlon Westkoff, Ruth Lichterman, Betty Snyder, Frances Bylas, and Kay McNulty.
All mathematicians.
Brilliant mathematicians. Initially hired out of the old job title of human computers, but when ENIAC was built, they were given the task of translating complex ballistic trajectory equations into the physical reality of the machine.
How did they actually do that? You mentioned there was no stored memory, so they couldn't just type code into a keyboard. How did they program a 30-ton machine without a manual?
They had to invent the entire methodology of programming as they stood in front of the machine.
Invent it from scratch.
Completely. They were handed schematic diagrams of the ENIAC's panels and had to figure out the exact physical switch settings and cable configurations required to route the numbers through the machine in the correct sequence.
That sounds incredibly physical.
Oh, it was. They physically traced the logic pads through thousands of cables, plugging and unplugging heavy black wires into patch panels to create the arithmetic circuits. They were the world's first professional computer programmers.
And yet, history seemed to forget them almost instantly.
Entirely. When ENIAC was publicly unveiled to the press in 1946, these 6 women were not invited to the formal dedication ceremony.
Unbelievable.
They were excluded from the celebratory dinner. In the photographs released to the public, they were often assumed to be mere models posing with the equipment. Their foundational contributions went uncredited for decades, only coming to light when historians began to recover their names in the 1980s and 90s.
They taught the cold metal to think, yet they were rendered invisible by the culture of their time.
It is a profound injustice, yes.
So, we have a machine that can perform calculations at the speed of light, but it requires 30 tons of equipment, generates blistering heat, and relies on thousands of fragile vacuum tubes that constantly burn out. If ENIAC was this massive heat-generating behemoth, it sounds like an evolutionary dead end.
Yeah.
It is practically unusable for anything outside a government laboratory. How did they escape that physical bottleneck to arrive at the devices in our pockets?
The transition required an entirely new understanding of materials. A computer built from vacuum tubes could never shrink beyond a certain point.
Because of the heat.
Yes. The tubes required glowing hot filaments to emit electrons, which meant they consumed vast amounts of power and generated tremendous heat, causing them to shatter or burn out constantly.
Right.
The breakthrough occurred on the 23rd of December 1947 at Bell Laboratories in New Jersey. 3 physicists, William Shockley, John Bardeen, and Walter Brattain, demonstrated a device roughly the size of a fingertip. They called it a transistor.
How does a transistor actually work differently than a vacuum tube? How does it switch an electrical current without the vacuum and the heat?
It uses semiconductor materials like germanium or silicon. These are materials that, depending on how they are treated, can either conduct electricity or block it.
So the material itself acts as the switch.
Exactly. By sandwiching different layers of these materials together, the physicists discovered they could use a tiny electrical current to control a much larger current flowing through the solid crystal.
Fascinating.
It performed the exact same logical function as a vacuum tube, acting as an electronic switch. But it did so entirely within a solid piece of material. It generated almost no heat, consumed a fraction of the power, rarely failed, and crucially, could be manufactured at increasingly smaller sizes.
That is a massive leap.
This invention was so fundamental that it earned them the Nobel Prize in Physics in 1956.
So the transistor allowed computers to become smaller and more reliable. But if you were building a powerful computer, you still need thousands or even millions of these transistors.
Yes, you do.
If you still have to physically wire them together, aren't you just making a smaller, more fragile rat's nest of cables?
That was exactly the next major bottleneck, known as the tyranny of numbers. A powerful machine required hundreds of thousands of individual transistors, and each one had to be manufactured, tested, and hand-soldered onto a circuit board.
Millions of fragile solder joints.
Yes, millions of potential points of physical failure. The push to solve this came largely from military aerospace requirements. The military needed guidance computers that were small enough to fit inside the nose cone of a missile warhead and robust enough to survive the extreme gravitational forces of a rocket launch. You cannot have hand-soldered wires snapping during a launch.
So how did they eliminate the wires?
By printing the wires and the components out of the same block of material. In 1958, Jack Kilby at Texas Instruments built the first integrated circuit.
The microchip.
Indeed. He placed multiple transistors and their connecting circuits onto a single, small piece of germanium. The following year, Robert Noyce at Fairchild Semiconductor independently invented a more practical version using silicon, employing a planar design that allowed the circuits to be photographically printed onto the silicon slice.
That changes everything.
It was the third generation of computing. The integrated circuit eliminated millions of hand-soldered connections instantly by compressing an entire circuit board onto a chip of silicon the size of a fingernail.
And I imagine this is what leads directly to Moore's law.
Precisely. In 1965, Gordon Moore observed that the number of transistors one could fit on a silicon chip was doubling roughly every 18 to 24 months, while the cost plummeted.
An exponential curve.
Yes. This steady, relentless miniaturization paved the way for the fourth generation of computing, the microprocessor. In 1971, Intel released the 4004. It was a single chip containing 2,300 transistors. It functioned as a complete central processing unit, executing 60,000 instructions per second.
To put that in perspective, the 30-ton ENIAC could do 5,000 additions a second, and less than 30 years later, a chip the size of a fingernail could do 60,000.
Exactly. The calculating core of a computer no longer required an air-conditioned room and a team of specialized operators. It made the personal computer possible, leading directly to machines like the Apple II in 1977 and the IBM PC in 1981.
When computation stopped being a classified government asset or a massive university project and became a personal tool sitting on a desk in the 1980s, how did that fundamentally change the human relationship with mathematics?
It altered our relationship by making the mathematics entirely invisible. When a computer was a room-sized machine, you had to deeply understand the math and the hardware to use it.
Right, you had to speak its language.
Yes. But when the microprocessor made personal computing possible, the goal shifted toward creating a graphical interface that a non-mathematician could understand. The mathematics didn't go away. It was simply pushed down beneath an abstraction layer.
So the computer became a medium.
Exactly. The computer ceased to be just a calculator and became a medium. And the natural next step, once you have millions of isolated personal computers, is to connect them. A solitary computer is a powerful tool. A computer connected to every other computer on Earth alters the entire trajectory of human civilization.
This began with ARPANET, didn't it? The network funded by the United States Department of Defense.
It did, yes.
I recall reading about the very first message sent over that network in 1969. It was between a laboratory in Los Angeles and one in Stanford. They were trying to type the word login, and the system crashed after the first two letters.
That's right.
So the dawn of global digital communication, heavily funded by the military to survive a nuclear strike, trips over the letter G and simply delivers the word low.
It is a rather perfect piece of irony. The system was designed to be indestructible, yet it collapsed under the weight of its very first attempt at a simple greeting.
A humble beginning.
Very much so. However, they restarted the system, and the underlying architecture proved robust. 2 decades later, in 1989, Tim Berners-Lee at CERN invented the World Wide Web. He provided a graphical, hyperlink-based interface that transformed this obscure academic and military network into a universal, accessible medium. Today, an estimated 5.4 billion people use that network daily.
And this brings us back to that pane of glass and the invisible math. When we look at the web, we see text, images, and video, but what is actually traveling through those cables?
Pure numerical abstraction. Every single pixel on your screen is just a set of numerical values denoting the intensity of red, green, and blue light.
So even a photograph is just numbers?
Entirely. Every piece of audio, every voice on a global call is a physical sound waveform that has been sampled tens of thousands of times a second and converted into a long string of numbers. When you send a message or request a web page, your intent is converted into binary ones and zeros.
And then it is routed globally.
Yes. Those digits are then routed through a global mesh of fiber optic cables, under oceans and through satellites, by computers making billions of invisible routing decisions per second.
The scale of what that invisible infrastructure has enabled is difficult to fully grasp.
It is foundational to the modern world. Space orbital trajectories, the management of global financial markets, complex climate modeling, none of it is possible without this abstraction layer. Consider the Human Genome Project.
Yes.
Between 1990 and 2003, scientists mapped all 3 billion base pairs of human DNA. Without immense computing power, pattern matching that sheer volume of data would have required centuries of hand calculation. Yes. Today, whole genome sequencing can be done in a matter of hours. The greatest achievement of the computer is not the complex mathematics it performs, but the fact that it performs them so flawlessly that the complexity entirely disappears from our view. It allows humans to interact with pure logic as if it were a visual, physical reality.
That is the crucial pivot, isn't it? By making the math invisible, the machine finally allowed humans to stop calculating and start creating.
Precisely.
We no longer have to hold the equations in our minds or pass pieces of paper across a room. We can simply request the outcome and use that outcome to paint a picture, sequence a gene, or write a novel. We built a machine to do our chores, and it gave us the freedom to dream.
It is a beautiful way to look at it.
But now it seems we are crossing another threshold entirely. We have mastered classical computing, the manipulation of those ones and zeros. Now the machines are beginning to learn on their own. What happens when binary isn't enough?
We enter the fifth generation of computing, defined by artificial intelligence and the dawn of quantum mechanics. Artificial intelligence was theorized in the very earliest days of computing. Alan Turing and John von Neumann both considered it, but it only began delivering transformative practical results in the 2010s.
Driven by the massive amount of data we now have.
Exactly. Driven by deep learning, a technique that involves training vast artificial neural networks on massive data sets. It gave us machine translation, advanced image recognition, and large language models capable of reasoning and generating software code.
And the scale of this now is just immense.
It is astonishing. By 2025, the scale is, well, it is unprecedented. Google's search algorithm processes over 8.5 billion queries every single day. AI systems are generating highly accurate predictions of complex protein structures, dramatically accelerating drug discovery.
But even these massive AI models processing billions of parameters still run on classical computers, don't they? They still rely on those simple binary bits, ones and zeros.
Yes, they do. They are bound by the same fundamental logic as the Mark I and ENIAC, just infinitely smaller and faster. Quantum computing, however, represents a fundamental departure from that reality.
How so?
It is not just a faster version of classical computing. It is an entirely different approach to computation itself. Quantum computers use qubits, which operate on the principles of subatomic quantum mechanics.
For someone who hasn't studied quantum physics, how does a qubit actually differ from a standard binary bit?
Think of a classical bit like a coin resting on a table. It must be either heads, which is a 1, or tails, which is a 0. It has to be in one defined state to be read.
Right, it's binary.
A qubit, however, takes advantage of a quantum property called superposition. Imagine that same coin spinning rapidly in the air.
Okay, spinning.
While it is spinning, it is not definitely heads or tails. It exists in a fluid state of probability, representing both states simultaneously. It is only when you stop the coin, when you measure it, that it collapses into a 1 or a 0.
But how does having a spinning, undecided coin help you solve a mathematical problem faster?
Because it allows the machine to explore exponentially larger solution spaces simultaneously. If you want a classical computer to find the correct path through a complex maze, it has to try every single path, one by one, until it finds the exit.
A linear process.
Yes. A quantum computer, by linking these spinning qubits together through a process called entanglement, can essentially flood the entire maze at once. It explores all possible paths simultaneously, causing the correct answer to mathematically amplify, while the incorrect paths cancel each other out.
And are we actually seeing this in practice yet, or is it still entirely theoretical?
The milestones are arriving rapidly. In late 2025, Google demonstrated a physics simulation using just 65 qubits that achieved a 13,000-fold speedup over the Frontier supercomputer.
Goodness.
And Frontier is the most powerful classical machine currently in existence. IBM has developed processors containing over 1,000 qubits. The scientific community recognized this definitive shift when the 2025 Nobel Prize in Physics was awarded for foundational work on superconducting quantum circuits.
So the science is solidifying. What about the industry side?
The economic implications are vast. In the first 9 months of 2025 alone, quantum computing companies raised nearly $4 billion in equity funding. Estimates suggest the quantum market could unlock up to $250 billion in value across industries that require complex molecular modeling, like pharmaceuticals and material science. We are moving from a deterministic, binary world into one governed by the probabilistic laws of subatomic physics.
It is difficult not to compare these modern supercomputers and these emerging quantum systems to the human brain itself.
It is a natural comparison.
When we look at the brain, we see roughly 86 billion neurons, each connected to thousands of others, forming 100 trillion synaptic connections. It achieves all of its processing on roughly 20 watts of power, which is less than a dim reading lamp requires.
Highly efficient.
Extremely. And from that low-power organic web of tissue, it generates consciousness. It retrieves memories layered with deep emotional texture. It produces imagination, empathy, and curiosity. The computer, by contrast, performs perfect, emotionless arithmetic billions of times faster than the brain ever could. It never forgets. It never distorts a memory because of a passing mood, and it never tires. It does exactly what we've built it to do. If we built this entirely to amplify our own thinking, what does it mean now that the machine can do things, explore solution spaces, and process data at a scale we simply cannot comprehend?
That is the ultimate philosophical question of our era.
Yeah.
If you trace the trajectory of the past 80 years, you see a profound evolution. The computer began as a blunt physical tool.
A monster of metal, as you said.
Yes, it was a massive arrangement of metal and wire designed specifically to solve the intolerably slow nature of human arithmetic. It was built because we could not compute artillery tables fast enough to win a war. Yet here we are, merely 8 decades later. We are now observing quantum processors achieve computational feats that, to replicate using classical traditional computing, would require more energy than currently exists in the entire observable universe.
It's almost frightening.
We built a machine to add and subtract, and it has become the primary medium through which human civilization communicates, stores its knowledge, and increasingly investigates the profound nature of reality itself. We use it to map our own genome and model the climate of our planet. As these systems begin to assist in designing their own hardware successors, and as they delve into quantum realms that defy human intuition, the boundary between the creator and the creation begins to blur. We are forced to ask, at what point does the device cease to be merely a tool, and where does a genuinely new, autonomous successor to human logic begin?
It is beautifully strange, isn't it? Humanity set out to build a machine purely to do its chores, to handle the heavy lifting of mathematics so we could rest our minds. But in doing so, we unwittingly built a mirror, one that reflects and amplifies our own intelligence back to us, revealing complexities we never knew existed. And it leaves me with one final thought. If these emerging quantum systems eventually simulate the physical world so perfectly that they can predict the behavior of every atom in a chemical reaction or the precise folding of every protein in a human body, do they merely describe our reality, or do they become a new reality of their own? The next time you sit in a quiet room and you touch the smooth pane of glass on your device, I invite you to pause for just a moment. Acknowledge the invisible world resting silently in the palm of your hand. Think of the millions of equations executing beneath your fingertips. Think of the ancient, silent legacy of the abacus. And remember the uncredited women standing in front of a 30-ton wall of cables, teaching the cold metal how to think. It is all still there, quietly waiting for you to tap the screen. Thank you for joining us for this deep dive into knowledge. We will have another quiet exploration waiting for you next time.